Good morning. Just cleaning up a mess here. Maybe from me, maybe from another teacher. I don't know. Okay, let's see who I got here. Welcome to Alicia and Oscar and Bella. Good morning, Feeny. Good morning, Louisa. Alex. Amina. And Chelsea. You can look behind me in the corner while you're waiting for others and see if you can answer this. When do we reach equilibrium if you're given that graph? Hopefully you can see it close enough to take a guess. If not, maybe I can move you over there while I'm waiting. Let's see if I can accomplish that. Obviously, I'm here at school today to do a demo. Get some stuff with me. My fancy studio. Maybe that's a little easier. Antonine is here. Thank you. I know a couple of folks can't be here. They have appointments and stuff. That happens. Ellie is here. Good morning. So I got like 3 to go because then I'll have all but the folks that aren't here. Okay, our goal today is to talk about section 2.2, more or less, which is about Le Chatelier's principle. I think we've covered 2.1, and we've covered some of the later sections as well with the way I do it. So now I think we're up to this. So 2.2. Le Chatelier's principle. I'm going to cover this demo. Penelope's here too. I'm going to cover this demo and really section 2.2. Then we'll see if you got some questions on chapter 1 or 2 problems, okay? But I want to do this first while I'm here and I have all the chemicals out ready for you here in W201. So let me write down that I got my Penelope. Anybody else? Okay, that's it so far. Very good. Yeah. Any others try and say hello? We can't see principal. Oh, that's true. Now you can. Okay, now you can't see the warm-up. Okay, for the warm-up, who's got it over there? For the warm-up, after how many minutes do you reach equilibrium according to the graph? And Sophie, good morning. Punch in some guesses. When do I reach equilibrium? Can we see enough? There's the graph. Good. Got lots of good guesses. Okay. Well, at a certain point, the concentration of A becomes a constant. And you can kind of guess where that is. My graph's not perfect. Maybe between 4 and 5. 4 is, let's see, here, maybe a tad more. Certainly by 5 I'm there, aren't I? So maybe 4.5 minutes, maybe 5. I might say 5 minutes. It'll be clear on the AP test when you have a question like this in multiple choice, okay? 5 minutes. So greater than 5 minutes. No, that would be less than. Greater than 5 minutes, you're at equilibrium. And of course, what we're going to look at today in our demo is something that has a color, an ion that has a color. And if A has a color, what's going to happen to the color after 5 minutes? So after 5 minutes, if A has a color, what will happen to that color after 5 minutes? Aiden is here. Welcome, Aiden. Exactly, Bella, whenever the line gets flat. So what will happen to the color of that thing after 5 minutes? Color, if A has a color, would what? Thank you, Aiden. It will stay the same. Why? Because it's at equilibrium. It doesn't mean the reaction has stopped, but it will stay the same, and others got that answer too. Thank you. Exactly good. All right. We'll need to think about that today as we do Le Chatelier's principle. Okay, shall we do it? Soupy. Okay, so I've got you up high on a big plastic bucket. So I'm going to have the board behind me here, and I may move you down when we get to our chemicals in a few minutes. But for now, let's talk about what Le Chatelier's principle says. I'm on page 8 for your info. The demo I'll do is not in Cheryl's book, as far as I know. But let's talk about the principle. So she says, a system at equilibrium when subjected, that's a nice word, when subjected to a stress. Now, what does stress mean in chemistry? We're going to find out. Okay, it doesn't mean you got a lot of testing next week. Page is 108. Okay, so a system at equilibrium when subject to a stress will shift to partially alleviate the stress. And restore equilibrium. So stress can mean a number of things. Let me let you catch up. Stress can mean changing the concentration in moles per liter or partial pressures see if you can still see that, kind of. Okay, so stress can mean changing the concentration or partial pressure of one of the chemicals. And interestingly enough, it's one of the reactants or products. When you and I talked about reaction rates, it was all about the reactants, okay? That they run how fast the thing goes. Turns out the products or reactants can affect equilibrium. We're going to find out today how that is. Lola's here. Thank you. Ute. And stress can mean changing the P or U. You've been in chemistry a while now. What else could stress out the system? What else could you change aside from one of the concentrations of the chemicals? Give me some conditions. What could you change here to stress out a reaction? Temperature, Bella, good, that's one. And somebody else? And Lola, pressure, right. I'm going to put here sometimes pressure. If it's all in solution, the pressure doesn't do anything, right? But if they're gases, pressure definitely does something. We'll find out what that is, okay? Soupy, I think we're ready for our, yeah, volume also, Alex, will change the concentration if you think about it. If I go, it's going to make it more concentrated or a higher partial pressure. So that, in a sense, Alex, is correct, but it reflects the concentration of the chemicals. But that, of course, will also be here it is, which is also a stress. So yes, and that's why. Surface area, yine, only Bella, surface area if it reflects the concentration of the chemicals. There's more surface area, sometimes there's more ready to react. So that would affect the concentration as well. But good, you guys are thinking today. Super. Let's go to our demo. You ready? I'm going to back you up a little bit. I'm going to put you down on the desk. Don't get all scared, because I got to show you some chemicals. And we need to, like, right on the board behind me as well. But you got to see them in front of you. So I'll do that. And let's begin. So our demo of the Chatelier's principle. Okay, let's do an example. We're going to add some of this stuff. Now, the label's really old. You might not be able to read it. So I'll read it. But it's kind of, check out the color. It's kind of brown yellow, all right? Kind of brown yellow color. And it's a solution, 0.1 molar of iron nitrate. But it's NO3, okay? So you know which nitrate it is. Plus, and out of that, folks, iron nitrate, what's probably causing the yellow brownish color? Okay? What's causing the yellow brownish color? Let's see if you know. Any guesses? What's causing the brown color in the iron nitrate? Which thing? That ain't really a hard question. Think about it. Hint, rust. Iron, thank you, Oscar. Exactly. So iron nitrate, okay? Iron 3 is causing the color. Okay, and I'm going to add it to concentration of potassium thiocyanate. Remember that? SCN minus, potassium thiocyanate. Okay, so here we go. I'm going to do this in a test tube, and I'm going to do it really inaccurately. Well, I'm just going to add some together because I need to do it quickly so you can see it. Okay, we'll start with my iron nitrate. I'm going to put that little test tube there. Okay, then I'm going to add some of the KSCN solution, right? The potassium thiocyanate solution. So you thought I was making up all those names. You really got to use them now in the course. Okay, and everybody watch. And wham! Whoa! It makes a really, 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 really dark red-brown ion. So clearly I get a reaction, okay? Clearly I get a reaction. Now, I diluted some of this stuff down, okay? A whole bunch so you can see the color easier. I added a lot of tap water, and I made then this concentration, okay? So you can see the color a little easier. So it's a nice red-brown color. Okay, now here's what you screwed up on in the last assignment, the last lab. Please write the net ionic reaction for this reaction now. So everybody, what's the net ionic reaction. Net, net, net. Not net, but net. Hint, remember who the spectators are. Don't put them in. Okay, go. You got a minute to do it. So whole reaction. You can type it in and or do it on your paper as well. So the left side you can guess for sure. No, the left side you know. So write down the reactants to start. You can probably guess the product, but you can definitely get the reactants if you leave out the spectators. Each of you has to be able to do this with confidence. Remember, you need to memorize the spectators so you don't put them into reactions where they don't do anything. Okay, type it in. You don't have to put it as superscripts and stuff, but just type it in. Good. Yeah, thank you, everybody, for doing that. Okay, let's see what we got. Iron. Yeah, I need some charges, though. Can you at least put the charges on stuff, even if you don't put it as a superscript? Just put the charge after it. Because if you don't put charges, it's wrong with a capital R. Okay? Just kidding. So Mina and Chelsea, Isabel, Bella, you're on the right, and Sophie, you're all on the right track, but add some charges, please. Thank you. Thank you, Anne Sophie. Okay, so let's start with her. So she's got Fe3 plus SCN minus, and that's really good. Okay, so I'm going to add some stuff to make it pretty. They're both, of course, solutions, so they're made with water. They're aqueous. And this stuff was the tan, or we could say yellow-brown. This stuff is clear. Okay, so turns out several of you guessed correctly what you make, and some of you did not. You actually don't have to balance it this time. So I understand why you did it, but it turns out it makes what's called a complex ion. So it makes this, just one of each makes Fe, SCN, 1 and 1. And then what will the charge be on that? Let's see if anybody figured it out. Nobody did yet. What would the charge be on? It's called the ferrothiocyanate ion. Or you can call it iron 3 thiocyanate ion. The charge on it. Yay, good. I love it. Your brains are on. Thank you, Aiden, Chelsea, Amina, Lola, and Sophie, 2 plus. So it's called a complex ion. Up until 3 years ago, you used to have to memorize 40 of them for the AP test. It was stupid. So they took that out. But this is one of them that is really kind of pretty because it's a nice red-brown, like we saw. And now we can start our demo. That was just sort of the beginning. We're going to start it now because we're going to do some stuff. And you're going to figure out which way the reaction shifts. So use this reaction. And now, I got to change one thing on it. We're going to make arrows going both ways. Okay? Can you make it? It's that way it's equilibrium, right? So even though this looks like it stopped doing anything, probably molecules are going back and forth. Some of these are breaking up. Some of these are forming. So some are forming, going forward. Some of the Iron thiocyanates are going backwards and are breaking up. Okay, so it's a dynamic equilibrium, even though it doesn't look like anything's happening, something probably is at the molecular level. Yeah? Sweet. So, away we go. I need a chart. And we're going to pull this back and forth, but I'll need you to see the bottom too. I don't need to see that low. I want you to see that equation too. Okay, so what we do, in other words, what's the stress we do in Shiro language, okay? Reaction will shift. Now, I'll be honest, I differ with Cheryl here. She likes to say right or left. I like to say towards the products or reactants. So, what color is the description for Fe? Yeah, it was the yellow, the kind of yellowish brown. There's this stuff, okay? Ah! Right. That stuff, okay? That's it. Okay, I want you to have 3 columns for our demo, okay? Here we go. So what we do, that's what we're going to call in Cheryl language the stress. Then the reaction will shift towards, and I'm going to use the word product or reactant. Cheryl will use right and left. We differ in our opinion there. And then finally, FeSCN2 plus, what happens to the concentration? Will it do nothing? Will it increase? Will it decrease? Okay, first stress. First stress. The chemicals. Maybe I got to elevate those. How can I do that? Like put them on the bucket. I'm not real fond of that. Is there something else I could put them on? Too high. Oh, that's not bad. That's not bad. Are they going to fall over? Yeah, they're going to fall over. Okay, that ain't bad. All right, stand by. I got to find something to put these on so you can see them. I mean, there they are. I made 1, 2, 3, 4, 5. They're not even, but 5 amounts of chemical. Once I watered it down, the FeSCN plus system. So 5 of that. We'll use 1 as like a control. That'll be maybe our control. And we're going to do something to the other ones and see what your prediction is, okay? All right, you need something to put it on. Old chemistry books. But of course, what do I use Zumdahl books for? We only have 1,000 of them. And I didn't like them in AP. And you need 1 more Zumdahl. Okay, here's the first thing we're going to do. I'm going to add more of this stuff. So we're going to add what? Fe3 plus. No, I'm not going to say add. I'm going to say increase. Increase Fe3 plus concentration. Okay, so I'm going to add some more of this stuff to what did I say? You can't really see the board now, can you? Drat. It's hard to get you to be able to see everything. Okay, well, let's add some more of this stuff. Here, I'm going to use a pipette this time, be a little more scientific, and add some to the first one, okay? Well, what's your prediction before I do this? Will it go towards the products or the reactants? In other words, will I make more FeSCN2 plus or will I make less if I add more of Fe3 plus? I'm adding more of this stuff. What do you think? Will it get darker? Will I make more red-brown or will it make less red-brown? That's the red-brown stuff. Waiting for some guesses. Once I see a few, then we'll do it. More product, more FeSCN. Good. Okay, good. And Aiden has a question. Well, we're not adding any KSCN. I'm just adding this stuff right now. So here we go. Ta-da-da-da-da. And I don't know if you can see the result, but I can. Can you see the change? Oh, yeah, you can see it. Check it out. Ready? Look at this one compared to the other one. It got, hooray, thank you, Anne-Sophie. It's darker. So you were right. We shifted to the products. And what did it do this? Well, of course, it increased it. So it increases. Beautiful. Let's do a number 2. And for our second one, we're going to add some crystals of this stuff. What is this stuff? Well, it is, in German, kaliumtiocyanate, or in English, some crystals of potassium cythionate. So add solid KSCN. Okay, studio audience, what's going to happen to the color? So I'm adding solid KSCN. Remember, there's your reaction. What will happen to the red-brown color? Make a little prediction. And while you're doing that, I'm going to get a spatula and get some crystals ready. We got a ton of this stuff. That won't be hard at all. I got a pretty good amount of crystals. There they are. So I got some guesses. I'll make some guesses. Which way is it going to shift, gang? Towards reactants or products? KSCN crystals. There's our first one. So we're going to now do the second one for that. All right, I got one guess is that it won't change color. KSCN crystals. Another guess is the same. Product won't change. Reactants. Shift towards the reactants. Reactants. Okay, let's find out. Here we go. Tell you what, let's just chuck it in here. No. In fact, it got really dark because I had kind of a lot. So everybody was wrong. Let's find out why. Sometimes you learn more from your wrong guesses than your right ones. It went towards the products. And so the SCN definitely increases. Or increased, whatever. Why? Okay, here's what's going on. I'm going to move this to the side for a second. Carefully. My people, if I add more of this stuff, I've got more of these particles in the solution. Much more. much more, lots and lots of these SCN minus particles. When they hit some of these, they're going to grab them and make more of this. It's just more likely to happen because I got more of these particles. I added a bunch of these in here. Just like in the first one, right? The first one I added more iron 3+ particles. And because there were so many more of that, they grabbed these guys and made more red-brown. Well, so it's the same reason here. If I increase either of the reactants, I'm going to make more product. Cheryl describes it as, what does it do to relieve the stress? Oh, I've got so much SCN minus. How can I use it up? Oh, God. I'm going to make more product. Now, that's a little melodramatic. Chemicals don't really have tantrums. So what I like to say is, which am I adding more particles to? And what's going to happen? It's all about probability, if you've studied that. If I add more of these particles, it's more probable they're going to then react with these guys and go over. If I could take some out, ooh, think about that. What if I take SCN minuses out of the system? Well, suddenly, it's more likely that these things, the products, will break up and form more SCN minuses to kind of replace them. Why? Because it's just more likely there's more of them there than if I took out some SCN minuses than there would be, right? So think of particles. Think of the particle model. More particles, more reactions going towards the product. If I took out a lot of this, in fact, if I just had pure red-brown and I didn't have any of these, probably a lot of these would break up to make more of these until it hit an equilibrium situation. Okay? All right, so I hope you learned something because I had a lot of wrong guesses there, but that's just the way it goes. Let's go back to our original and let's see if we got questions. Yeah. Good. Okay, so question from Penelope is, what about the potassium? If there's potassium with the SCN, well, minus, the product would still increase. Yes, and here's why, Penelope. Notice in the net ionic reaction, Penelope, you and others wrote, and you wrote it correctly, K plus is not in there. Turns out K plus doesn't matter. I could add a bunch of K plus, and guess what? It doesn't affect anything. It's not in the reaction, as it turns out. So even though, Penelope, it's in the original chemical, it's not doing anything. It's a spectator. Exactly, Amina. K plus is just a spectator. Yes, exactly, Anne-Sophie. Good, good. Yeah? Okay, let's do one more thing. Okay, I'm going to add some of this solution. You ready? So I'm going to add some okay, H2PO4. That's weird. We got to think about that. So really, I got to tell you, or I got to ask you, part of that chemical is soluble. Part of it's not. What's going to fall off and not really be part of this interesting story? What's not going to do anything out of this chemical? What's not going to do anything out of the chemical? Yes, careful. Anne-Sophie and Bella, careful. There's no K in the world. It's just not out there. There's only K plus. I know I'm picking. So what's left? Really what we're adding is H2PO4 minus. Okay. You know what? I think this time we're going to do it and then have you think about it. Yes, Anne-Sophie, but what charge is on it? Figure it out. H2PO4, what charge? Okay, so we had the first one, we added more Fe3 plus. The second one, we added more SCN minus because it was in the little crystals I added. And let's find out if Anne-Sophie is right and what happens here when I add some of this. Holy moly, Batman. Look at what's happening. It's clearing up. It's clearing up. Anne-Sophie, I think you were right. In fact, I don't even have to add any more. Look at it. I'm going to do this with my thumb. Remember I told you how to mix that with your thumb? Oh, look at that. It's gone. Holy moly. Well, that's a fine kettle of fish. Look at that. So somehow, Errol is there. Got everybody. Okay, so somehow something's happened here. The color disappeared totally. Why? Why is exactly my question too. Good, Anne-Sophie. Now let's ready to think about why that is. So clearly, we had something else happen. Well, did we favor the products? No products at all. Well, for sure, what happened with the concentration of the FeSCN2 plus, gang? The concentration of this stuff did what? Just so I know you're following. What happened to the concentration of FeSCN2 plus? It Thank you, Oscar. Clearly decreases to the point of like nothing. Okay. Well, that's interesting. Let's see if we can figure out why. Okay. All right. Man, look at it. It's totally gone. Here was the original, by the way. In fact, I got two originals, two controls. Forgot. So 2 controls, that was adding extra Fe3 plus, adding SCN minus, and then adding this new chemical. Well, the best way to figure this out is to write a reaction. So let's answer Anne-Sophie's question, and a lot of you, why did this happen? Okay, so here it is. H2PO4 minus. And there's my original reaction. Oh, there it is up here. Well, what do you suppose it would react with? It could react with what? H2PO4 minus could react with what? Either or What could that be reacting with in my reaction? It could react with the Fe3 plus, or not really, Bella. Could react with who else? Or, right, could react with the FeSCN2 plus. Exactly. One or the other. Now, which should have the more powerful attractive force? Which of the two that you've said? It would probably react with the one with the greater attractive force. Which chemical would that be? So this will probably react with which one? Use your knowledge. Which one will have more attractive force? Yeah, that's a hard question, but you can do it. Look at the two possibilities you had. So will it be the Fe3 plus or the FeSCN2 plus? Which one has more powerful force of attraction? Fe. Well, there is no Fe, Alex. What do you mean? Ah, okay. Fe3 plus. Yeah. Why? Because it's a greater charge. And so a greater charge would be more attracted to this. And what I'll get is FeH2PO4. And this one actually is something I got to balance. So I got to have 3 of these suckers. And I need to have a 3 down here. And I believe it forms either a solid solution or a solid. I don't know if we can see that at the bottom. Nah, not much. I don't know if I see any solid down there, but I think it is forming a solid. At any rate, let's see what that does to our solution. So essentially, I grab the Fe3 plus and do what with it in my other solution? What am I doing essentially with the concentration of Fe3 plus, gang? So the Fe3 plus concentration, remember we do with brackets, does what? It decreases. Thank you, Bill. So Fe3 plus concentration decreases. And this is the part that gets cool. You ready? So it's like I'm digging a hole. You ever dig a hole in a pool? Try and dig a hole in a pool. What happens? The water fills back in. Well, what's going to happen here? Ready? Dig a hole, dig a hole, dig a hole. Well, there's less of this. So what are these guys going to do? They're going to break down and fill in. But you know what? All of them are taken out. All of them taken out. Oh, man. All these break down. Isn't that something? All of them break down. And eventually the Fe3 plus is taken out of commission. You don't even see it anymore because of the situation it's in. Isn't that kind of cool? So really, if I add this, what this really does is I decrease the concentration of Fe3 plus. And so, of course, it'll shift to the reactants. So it shifts to reactants. I can say, but the Fe3 plus is eliminated. I could say it goes to 0 moles per liter. It's taken out of there totally. I did that in the demo to make it a little more interesting and a little more challenging for you. Let me stop and pause and see if you have questions on this demo. So sometimes the unexpected can also be explained, right? We're pulling something completely out of the system, and then there's no color left. Thank you, Oscar. Okay, so I'll try and make it so you can see, and I'll get out of the way, and I'll read it. Okay, so I wrote here, for this third thing, it does shift to the reactants, but then the Fe3 plus concentration, Oscar, goes to 0 moles per liter. So yes, we have no products at all. That's the first thing I read, but we also have no Fe3 plus at the end of the day either. So we have, first the products all go backwards to the Fe3 plus. It happens really quick, but then the Fe3 plus is just totally encapsulated, so to speak, by this other ion, and it goes right out of solution. And this stuff obviously is what? Colorless. So I make something that's completely colorless, therefore everything's gone. Good question. What happens to the SCN minus, I think you mean, on the product side when the Fe moves to reactants? Well, guess what? The SCN minus is probably still where, Aiden? I can't see them because they're clear, but I bet there's a bunch of SCN minuses still floating around because they're not in this chemical we made. So they must still be SCN minus ions floating around, and those suckers are also clear. And even though I have it in a brown bottle, it's actually a clear solution, the KSCN, so the SCN minus source, it's clear. So they're still there, Aiden. Another question. Let me try and read the last part of your question. Would the Fe3 plus ion from the broken down product also be removed? Yes. So what's happening instantaneously, Anne-Sophie and everybody, is that these, in our original reaction, the products are being broken down to replace the Fe3 pluses that are getting caught up in this new compound. So we're breaking down, but as soon as they get over here, they're used and pulled out. So it's like the hole never gets filled, just like in a pool. Make a hole in the water, other water just fills in. In this case, other water fills in until the water is all gone, till all of this stuff is gone, totally broken down. Equilibrium's kind of cool, huh? So you can play with a reaction like this, make it go back and forth. Yeah? I can also add some more. What else did I do? Just for grins. What's that? Since we got a little bit. I added SCN crystals and made it browner. What if I add some SCN solution? If I don't spill it all over myself. Yeah, that made it browner too. So solution or crystals doesn't matter. If I add SCN, then SCN minus source, then it pushes it towards the products. So both of those got darker. More SCN minus from crystals that dissolved, and here SCN minus from the solution still pushes it towards the products. That, if you can understand the Chatelier's principle, you got a lot of things that you're going to be just fine at in this class, okay? All right, let's put you back up on the pedestal so you can see more of the board. Good. I took a lot of time for that, but it's worth a lot of time. Let's see if you got some questions in the remaining 12 minutes, okay? So anything you want to ask about in chapter 1 or 2? You got any questions? We might have time for 1 or maybe 2. I'm going to make some board space up on the top from the beginning of the hour because we're done with that. Any you want to ask about chapter 1 or 2? If not, I have more I can tell you. Okay, while you're thinking, I'm going to give you a little Cheryl diagram. So page 112. She calls this the equilibrium 1 and equilibrium initial and equilibrium final. I want to show you what she's talking about here. So I got 2 SO2, these are all gases, plus O2 forms, 2 arrows, 2 SO3. Now it says we're going to remove SO2. Remove SO2. Okay, well, here's your initial equilibrium. EI for initial. I'm just going to make it like she does with big flipping arrows. You ready? Okay, so I'm on page 112. So she says, okay, I got an initial forward that's going to look like this. My initial reverse can look like this. How to know how long to make it? It's kind of random. She just picks something. Now, what the system does to change it, she writes as S, or you could call it the stress. So here's the stress. Oh, what happens? So is it stress or system? What does she want it to be? She says it's stress. Okay. Well, the stress, if I remove this, then it's going to go which way, gang? It's going to go more towards the what? If I pull out this stuff. What were we just saying about pulling out of water in the pool? It's going to move towards the reactants or products more. Okay? Which way is it going to go? More reactants or products? If I take out the SO2, it will shift towards the reactants. Thank you, Ellie. Thank you, Oscar. So what that means is the reverse reaction is going to be bigger for a little bit. So it's going to be, or she's got to be in the same. Well, let's leave it the same. It doesn't matter. So the reverse reaction is going to be going on, but I'm going to have less of the reaction going forward. Why? Because I've got less of these that are there. So there's less particles of SO2 that can react and make product. So my forward reaction is a shorter arrow. So that's what that means. So draw yourself a little note. So shorter, so less forward reaction or slower forward reaction. Maybe I should say slower forward reaction. So what that means is when I reestablish equilibrium, so I get a new equilibrium after that, so we'll call it the equilibrium final. I've got the arrow in the system shifted over a bit. So now I can make a few more of these, but it's never going to be this long. The whole system's going to be shorter. So these are equilibrium initial. I got some arrows. Stress, oh, I got less forward reaction because I'm pulling this out. And then the final is when it reestablishes equilibrium, the forward's less and then the reverse adjusts and is less as well. Isn't that wild? So it ends up changing both the forward and reverse reaction rates eventually. So if I pull out one chemical, it can affect other ones, and it affects then the forward and reverse rates that are going on, okay? That's what those arrows are about in Cheryl Smith's book, page 112. Okay, that we did before, you don't need that. And let's talk about temperature and pressure. So let's go a little bit to page 120. We're on 2.3, more or less. I don't know if she's going to talk about this, but I'm going to use it for this. So page 121, I'm going to use her reaction. It looks like this. PCl3, and these are all gases, I think, goes to Cl2. Whoops. Cl2. No, plus Cl2, pardon me, forms PCl5. Okay. Shall I go against her? Okay, she wants to do pressure. All right, we'll do pressure first. Okay, so squeeze this. In other words, now we're going to do what somebody said earlier. I think it was Alex said volume. So we're going to take it and go. Here's what happens if I squeeze a system. If I take a bunch of gases, these are all gases now. Gas, gas, gas. If I squish it, then the particles are more likely to react because they're closer, and I end up making whichever side has less moles of gas. So if I squeeze it, it's going to be forced to make less, something that takes up less space. That's the way to think of it. So squeeze this, and chemicals will react to the stress by taking up less space. Here's your analogy, right? You and a friend are on the S-Bahn, and you're sitting across from each other, right? And then two other people come, and they want to sit there too. So you got to what? You got to scrunch together and make it up. You got to take up less space so there's more room. So you got to, if you're put under pressure, you got to take up less space. So that happens to molecules too. So look at this. Which side, reactants or products, would take up less space? Check this out. Which side, gang, reactants or products, would take up less space? What's your guess? Which side would take up less space? You still out there? Yeah, kind of. I got some of both guesses. And yes, products is correct. Why? Because I got 1 mole of gas. And here I got 2 moles. Oh, I got a mole of PCl3 and a mole of Cl2. What that means is there's twice as many particles. Here, twice as many particles. Here, less particles. So, aha. Reaction shifts towards the side with less moles of gas. Isn't that cool? That relieves some of the stress, some of the pressure. Isn't that cool? So all you got, so here, that's the products. But it's not always the products. So squeeze it. Oh, I got to go to less moles. I'm going to go to the products on this reaction. All right? That's only true for gases. So Achtung, if it's all solutions, you don't have this problem, okay? So only if gases are involved. If it's solutions, no way. It doesn't really change anything. We're going to stop right there because I only got a minute left. But we're right in the middle of 2.3, and that's a pretty good spot to be. If you have an individual question, you can always type and ask me too. But I'll see you tomorrow as well. Could I move the camera a little bit? Sentences are cut off. I think I moved it so you got it now. I'll look and see. So, aha, the reaction shift towards the side with less moles of gas. Here it's the products. And only if gases, sorry, plural, gases are involved. We'll see you tomorrow, gang. So I'll send this video out as well in case you missed something. Stay healthy. See you then. Bye.